Put your hand flat on a table. It feels solid. It feels stuck. But right now, the particles in your hand are attempting to pass straight through that table. Billions of times every second. Almost all of them fail. But not all. Some of them actually make it through. This isn't science fiction. It's called quantum tunneling. And it's happening inside your body. Inside the sun. Inside the chip running this video right now. It is one of the strangest things in all of physics. And without it, you would not exist. In the everyday world, the rules are simple. A ball rolling toward a hill needs enough energy to reach the top. Not enough energy? It rolls back. Always. This is the classical rule: you cannot pass a barrier you don't have the energy to climb. It's common sense. It governs everything you can see. But particles do not follow that rule. Because a particle isn't a tiny ball. A particle is a wave of probability. And a probability wave can do something a ball can never do. It can leak. To understand how, we need the wave function. In quantum mechanics, a particle isn't at one definite place. It's described by a wave, a mathematical object encoding the probability of finding the particle at any location. Where the wave is large, the particle is likely to be. Where it's small, it's unlikely. Now, send that wave toward an energy barrier. In the classical world, the particle stops dead. But the wave doesn't. Inside the barrier, the wave doesn't drop to zero instantly. It decays. Exponentially. It shrinks fast, but it does not vanish. And here's the key. If the barrier is thin enough, the wave still has a small, non-zero value on the far side. A non-zero wave means a non-zero probability. Which means there is a real chance the particle is simply there. On the other side. Without ever having had the energy to climb over. Now here's the part that breaks people's brains. The particle never had enough energy to be inside that barrier. According to classical physics, the inside of the barrier is a forbidden zone. To be there, the particle would need negative kinetic energy. And negative kinetic energy is impossible. So the particle should never be inside the barrier. And yet, it comes out the other side. It doesn't climb over the top. It doesn't smash through. It's as if it crossed a region it was never allowed to enter. Think about that. The particle crosses a zone that, by every classical law, it cannot occupy. Nature doesn't ask permission. The mathematics simply says, there is a probability. And so, sometimes, it happens. This is not a curiosity. Quantum tunneling runs the universe. Start with the sun. For the sun to shine, protons in its core must fuse together. But protons are positively charged. They repel each other, and that repulsion creates a barrier. Here's the shocking part: even at 15 million degrees, the protons in the sun's core do not have enough energy to overcome that barrier. By classical physics, the sun should not be able to fuse hydrogen at all. It only works because protons tunnel through the barrier. Without quantum tunneling, the sun would not shine. Stars would not exist. You would not exist. Now come down to Earth. The scanning tunneling microscope, the device that first let us image individual atoms, works by measuring the tiny tunneling current of electrons across a gap. The flash memory in your phone stores every photo by tunneling electrons through a thin insulating layer. And radioactive alpha decay is simply an alpha particle tunneling out of a nucleus it could never classically escape. This bizarre effect is woven into the fabric of reality. And into your daily life. There's a deeper lesson hiding in all of this. The universe is not deterministic. It is probabilistic. The barrier doesn't have a secret door. There is no hidden mechanism that lets the particle through. At the smallest scale, reality simply runs on probability. And given enough chances, even the impossible becomes inevitable. But tunneling also sets a hard limit on our technology. As computer chips get smaller, the components inside them get closer together. And when they get close enough, electrons start tunneling between parts that are supposed to be completely separated. This causes current to leak where it shouldn't. We are now building transistors only a handful of atoms wide. And we are running directly into the quantum wall. The exact same effect that lights the stars is what may finally bring an end to Moore's law. The thing that makes the universe possible is the thing limiting our most advanced machines. Quantum tunneling is proof that reality is stranger and more generous than our intuition allows. The walls we think are solid are really just very high probabilities, not certainties. Nothing is ever truly forbidden, just unlikely. Next up, the measurement problem. Why does observing a quantum system change it? Why does the act of looking force reality to choose? Subscribe so you don't miss that one. And tell me in the comments, does a probabilistic universe make you uneasy? Or does it set you free? I genuinely want to know.